Hello, our group is G4-F. Our group consists of 4 members, which are Lim Lichi, Nur Zahira binti Kamaluddin, Azman Hashim Ismail Darwis, and myself, Muhammad Hafiz bin Atikun. Our contents are divided into 5 parts, which are Introduction, Reaction Engineering 1, Process Modeling and Simulation, Separation Process 2, and also Conclusion. Moving on to Introduction. Hydrogen production. Hydrogen atom is composed of one proton and one electron, making it the lightest element in the universe. Hydrogen is the simplest and most abundant element on Earth. Hydrogen gas can be produced from hydrocarbon fuels through basic technologies such as steam methane reforming. Moving on to our overall process. Our overall process are divided into 3 parts, which are SMR reactor, CO2 removal unit, and H2 enrichment unit. SMR reactor are specifically for reaction engineering 1, while CO2 removal unit are for process modeling and simulation, and H2 enrichment unit are for separation process 2. Moving on to reaction engineering 1, the reactions involved consist of 2 reactions, which are steam methane reforming and water gas shift reaction. SMR is a first reaction, while WGS is a second reaction. The temperature for SMR range from 800 to 1000, while the temperature for WGS are from 200 to 400. The pressure for SMR is range from 20 to 35 atm, while the pressure for WGS is from 10 to 15 atm. Next is type of reactors used. For the reaction process to occur, catalyst is involved in the reaction. Hence, packed bed reactor is chosen as the reactor to operate both of the reaction. This is because inside the reactor, there is a catalyst bed in the middle part of the reactor.
To calculate the kinetics data, differential method is used, where we can derive this equation from the basic mole balance equation of the packed bed reactor. By using this equation here, we can draw a linear straight line graph. For steam methane reforming, the reaction formula is shown here, where methane reacts with steam to produce carbon monoxide and hydrogen. The limiting reactant here is methane, while the catalyst used is NiOAl2O3. Reference values were taken from the article to calculate the Ca0 by using the ideal gas law. Temperature equation here is derived from the energy balance equation, and we can write it in terms of the X conversion. By that, we calculated Ca and non-Ca at different X. The graph on the left is taken from the article, where we can get conversion of methane X at different space-time, and a table is tabulated on the right. By plotting the graph here, we would get the dW over Fa0 dx of different X. And after plotting this graph here, we can get a rate order of 2.2319 and the rate constant K of 9620.004. Moving on to the water gas shift reaction, the reaction formula is shown here, where carbon monoxide is reacted with steam to produce carbon dioxide and hydrogen. Limiting reactant here is carbon monoxide, while the catalyst used is Fe2O3. The calculation steps are similar to the previous SMR, just that the Ca0 here is different, where it is the outlet concentration of CO at the SMR. From the graph here, we can get the conversion of CO and the space-time, and similar steps were taken like the SMR. For this part, it is also the same as the SMR reactor. By plotting the graph here, the rate order that we get is 0.6906, while the rate constant K is 1.269. For the strategy to maximize the selectivity and yield of hydrogen, catalyst concentration should be high because it increases the rate of reaction. For gas hourly space velocity, it should be low because methane conversion will increase in that way and more hydrogen will be produced. In terms of temperature, because of the reason here, SMR should operate at a high temperature because it's an endothermic reaction. Well, because WGS is exothermic, so it favors a lower temperature. As for pressure, due to the reason here, the operating pressure for SMR should be lower, but WGS is not affected by pressure. To calculate the sizing of the reactor for SMR, numerical integration method is used from x equals to 0 to x equals to 0.79. This table here is tabulated where t is in terms of x while k is affected by t. By using the 5 points quadrature formula, the weight of catalyst can be calculated, where in the end we get 13,347.54 kilograms of catalyst. As for the volume of SMR, it can be calculated by dividing the weight of catalyst by the bulk density of the catalyst, where in the end we will get 7.138 meter cubes. For WGS, the same method is used, which is numerical integration method, from the x equals to 0 to x equals to 0.95. And this table here is tabulated. And by using the 5 points quadrature formula, the weight of catalyst is calculated, which is 38,271.3 kilograms of catalyst, while the volume of the WGS reactor we get is 33.28 meter cube.
Hello everyone, my name is Azman Hashim bin Ismail and I'll be talking about the process modeling and simulation part in this presentation, or the absorption process to be more specific. Now before we go into the absorption part, in the effluent stream or WGS, in the next slide in table 1, in the composition it contains water vapor. Now to ensure that we have no issues with the absorption process, we have decided to completely remove the water vapor as stated here. Now, in order to do that, we send the stream into a condenser, which cools the stream down to 40 degrees, where water is assumed to be fully condensed and removed. And in this slide here, we show both compositions of before and after water removal in table 1 and table 2 respectively. Now onto the absorption process. Our absorption process the CO2 removal unit consists of an absorber tower as well as a stripper tower. And as shown here in the diagram, that's how it looks like. It contains a pump, it contains a heat exchanger, it contains a condenser for the CO2 gas, and so on. So it is stated here our operating conditions for the absorber is 40 degrees Celsius and 1 atm. And the amine solution we use is a 30 weight percentage of MEA solution. Now we want to have a 90% CO2 removal to ensure that the adsorption process has no issues, and we chose 90% because it is a logical number, and because 100% removal is not possible. Now the stripper operates at 120 degrees Celsius and 1.8 bars of pressure. Now, as our amine solution MEA at 40 degrees Celsius has a CO2 loading capacity of 0.5 mole CO2 over mole MEA. Now, the diagram shown on this slide here is our material balance for the absorption process. Now, since 90% of CO2 is to be removed, therefore, the molar flow rate of CO2 in the stream Ln plus 1 should equals to 90% of the molar flow rate in stream Vn plus 1. Now, based on the calculations here, we managed to get the amount of molar flow rate of CO2 to be removed, and by using the MEA CO2 loading capacity, we are able to calculate the amount of moles of MEA required to remove the CO2. Now, assuming that the molar flow rate of MEA in stream Ln plus 1 is equals to stream Ln, Therefore, we can say that the molar flow rate in MEA molar flow rate is the same in Ln. Now, in order to find the total molar flow rate of stream Ln, we convert the weight percentage into molar percentage using the equation shown. And once we have the molar percentage, we can find the total molar flow rate of Ln. Now, since 90% of CO2 is removed, we have to calculate the new CO2 molar flow rate in the exiting gas stream of the absorber, which is Vn. Now we can calculate it by multiplying 10% with the initial molar flow rate of the of CO2 in the gas stream. And once we find that, we can find the new total molar flow rate of the exiting gas stream of Vn, which is shown below as well. And finally, in this table here, we can see the new molar flow rates as well as composition of the exiting stream of the absorber. That is all. Thank you.
For separation process 2, the main focus is on hydrogen enrichment unit. Therefore, we are required to determine the type of adsorbent used. So in our group, the type of adsorbent used is 13X zeolite and BPL 4 times 10 activated carbon. So here is the characteristic of the adsorbent, which is particle density, particle size, particle porosity, micropore volume, and average pore diameter. So actually we have compared the differences between 13X zeolite and zeolite 5A, which one is better to be used. Therefore, we have found that 13X zeolite is much more suitable to produce 99.9% hydrogen purity. Next, we need to determine the adsorption isotherm. Therefore, for the adsorption isotherm used, the Langmuir and Freundlich isotherm models were used to correlate the adsorption isotherms. After the collected data and information we gained from the articles, it was found that Langmuir model showed the best fit for the zeolite 13X, and Freundlich model provide excellent fit with activated carbon. So this is the picture of the experimental adsorption isotherms in BPL activated carbon at different temperatures. And for A is the adsorption of hydrogen, B is adsorption of methane, C is for carbon monoxide, and D is for carbon dioxide. So the other picture is the experimental adsorption isotherms in 13X zeolite at different temperatures. Next is the design of adsorption column. So here is the parameters that we gained from the articles, which is bed radius, bed length, reactor diameter, bed porosity, adsorption temperature, and adsorption pressure. So the value for bed length is 8 meter, the reactor diameter is 1.6 meter. So there will be a 4-column PSA cycle of adsorption towers that has been considered, and each column for the first layer contain BPL activated carbon, and followed by the second layer with 13X zeolite pellets. So actually the initial bed length is 8 meter, but after the scale up design, the bed length increased to 10 meter. Lastly is the strategy to achieve 99.9% of the hydrogen production and desorption process. So our strategy is to generate the BPL activated carbon and zeolite 13X. The method that we use is heating, which is we use to heat gas to a very high temperature overnight at 423 and 623 Kelvin respectively under helium flow. Next is the adsorbent bed is placed inside a stainless steel column surrounded by 2 stainless steel spiral tubes, and it is used to preheat the feed gas and control the bed temperature with a thermostated valve. The next step is the column and the surrounding spiral tubes are covered by an electrical coaxial furnace to control the bed temperature between 25 and 600 degrees Celsius. And lastly, the arrangement of
Adsorbent, which is on the first layer of column, is PPL activated carbon particles followed by the second layer of 13X zeolite pellets.
Conclusion: from all the assumptions, calculations that have been provided above, we are proud to consider that our group has successfully managed to solve the problems from the project given.